Um, okay. I hope everyone had a good exam and it wasn't too hard. Uh, I'll try to finish grading by the weekend because um, these are the last 2 weeks now, right? I will not cover any new material after the fourth, so fifth will be just a revision day for you guys, okay? To go over the important concepts and everything. So most of the new material is going to be covered this week and maybe Monday. Okay, Monday, and like I'll cover very little new material on Tuesday, if any. Okay, so let's start with chapter 5, derivative or differentiation. So that's the chapter name. And let's start off with the derivative of a real function. This is something most of you have seen before, so I won't be doing it in full details. Well, derivative of a real function. Okay, definition. Let f be defined and real valued. Defined and real valued on AB. Okay, so for now the function is from reals to reals. This is not defined on random metric spaces as of now. Okay. For any x in AB, uh, okay, say phi of t is equal to f of t minus f of x over t minus 6. Okay, and define f prime of x is equal to limit t approaches x phi of t. Okay, you're probably familiar with the definition of derivative, provided this limit exists. Limit exists. Okay. Then f prime is called the derivative of f. Then f prime is called the derivative of f at x, and we say uh, and we say f is differentiable at x. Okay. If f prime exists for every x in AB, which is a subset of E, well, for every E subset of AB, then say f is differentiable on E. On E. Okay. So since this is a limit right? You can define the right hand and left hand limits, and similarly, you can define right hand, left hand derivatives, but we are not going to go into that necessarily right now. Okay, so one important consequence of that is the fact that um, if you define right and left hand derivatives, then you can actually define the derivative at A and at B. So this would be right derivative, right derivative, left derivative, if the limits exist. And in that case, we can define right derivative and left derivative. However, in general, they are not said to exist, because the proper definition is the total limit has to exist, and the limit does not exist for A and B, right? The function is only defined on the interval. It's not defined on anything left and right of A and B. So we don't say f prime of A and f prime of B are defined. Okay? So not defined with our definition. Okay. Theorem 5.2. Let f be defined on AB. Then f is if f is differentiable at a point x, if f differentiable at a point x in AB, and then f is continuous at x. Proof. Okay, I'm not going to prove things using the epsilon delta definitions. For like, as epsilon delta definition for limit exists, you can technically define derivative using epsilon delta. I'm just going to go through with the limit definitions. As t approaches x, we have, by theorem 4.4, where product of limits exists, I have that f of t minus f of x is equal to f of t minus f of x divided by t minus x multiplied by t minus x. Well, this is going to f prime of x, which exists by definition. And is finite. Okay, so it is, while the book does not necessarily say the limit has to be finite, I'm going to say we say the limit exists of if and only if it is finite. Okay, so the limit exists and it is finite. Give me a second. So f prime of x times 0 is equal to 0. Okay. Note, converse is not true. Note, converse is not true. Is Not true. Continuity does not imply differentiability. Continuity does not imply differentiability. Example, f of x is equal to absolute value of x is not differentiable at 0, even though it is continuous. Even though it is continuous. Okay? So what properties do hold true? What can we say about differentiable functions? Theorem. Five point three. Suppose f and g are defined on AB. Defined on AB, and both are differentiable. And are differentiable at least at a point x. At a point x belonging to AB. I'm not asking for too much. I'm not saying in general. At least at the point AB. Then f plus g, f multiplied by g, and f divided by g are differentiable at x. Are and a f plus g prime of x is equal to, well, this is the nice one, f prime x plus g prime x. B, this is the not as nice one, f prime f prime x g of x plus g prime x f of x. And the worst one. Minus g prime of x f of x over g squared of x. Okay. With if g of x not equal to 0. Okay. Proof. A. So now we are again going to be using properties of limits rather than epsilon delta definition proofs. A follows from theorem 4.4, which implies limits can be added. B, let h of x is equal to f times g, and then h of t minus h of x is equal to f of t times g of t minus g of x plus g of x times f of t minus f of x. And now you divide by t minus x. Divide by t minus x. Note that as t goes to x, f of t goes to f of x, and, well, I don't need g of t going to g of x. F of t goes to f of x by theorem 5.2, which is just the previous theorem, because we are saying that, because f is differentiable at x, it is continuous. So as t goes to x, f of t goes to f of x. For c, let h of x is equal to, again, f over g in this case. Then h of t minus h of x over t minus x is equal to 1 over g of t times g of x into g of x times f of t minus f of x over t minus x minus f of x times g of t minus g of x over t minus x. Did I make a mistake? I think the first one should be g of t, not g of x. Yeah. And the book has a typo, and I blindly copied it. I knew one of them should be the other way around. G of t. Okay. Apply again. Letting t goes to x. And applying theorems 4.4 and 5.2, we obtain C. Okay. So that proves that result. Okay. Note, this technically does not say anything about f minus g, right? But we can show this for f minus g by noting that every constant function is differentiable, and so -1 is multiplication by -1 is differentiable. Note the derivative of any constant function is 0. Okay. Hence f minus g of x is equal to f plus -1 times g of x is also differentiable. Also differentiable. Okay. Another remark or note. Remark. if f of x, if f is defined, if f is defined by f of x is equal to x, then f prime of x is equal to 1. Okay? This does not mean that a very common mistake that people make is this means that, oh, the derivative at if the function's value at x is x, then the derivative is 1. No. For example, just because f of 0 is equal to 0, that does not mean the derivative is going to be 0. Sorry, the derivative is going to be 1. It depends on the function. If the function is f of x is equal to x everywhere, then the derivative is 1. Okay? Well, if f of x is equal to x, then derivative is 1, and then repeated applications of b and c. Applications of b and c show that x to the n is differentiable, and its derivative is n x to the n minus 1. Okay? Therefore, every polynomial is differentiable, and so is every rational function, and so is every rational function. Well, except at points when the denominator is 0. When denominator is 0. Okay? Now let us look at the chain rule of differentiation. Okay? It is quite an important tool. Theorem 5.5. Suppose f continuous well, continuous on AB, and f prime exists, and f prime x exists at a point x at some point x belonging to AB. Okay? Well, there shouldn't have been an A. Let G be defined on an interval, be defined on interval I, which contains the range of f, which contains range of f and G is differentiable at a point f of x. And G differentiable at point f of x. If, again, h of t is equal to g of f of t, okay, not again, well, I meant that I'm using h as the composition, as h as the total function, then h is differentiable at x. H is differentiable at h of x, and h prime of x is actually equal to g prime at f of x times f prime of x. Okay? Proof. Let y be equal to f of x. Okay? Then by definition of the derivative, I have that f of t minus f of x over t minus x, which is I have multiplied to the other side, is equal to f prime of t plus u of t. Okay? Because in the limit they're equal. They don't have to be equal otherwise, right? There's some small amount u of t which should go to 0, right? As t goes to x. Similarly, g of s minus g of y is equal to s minus y and g prime at y plus v of s, for another function v which should again go to 0, where t belongs to ab, s belongs to I, and u of t goes to 0 as t goes to 0, well, t goes to x, and v of x and v of s goes to 0 as s goes to y. Right. So now, because f is continuous at on a and b, I can say, well, let s is equal to f of t. As t goes to x, f of t goes to y. So it does satisfy the condition of x. Then h of t minus h of x, which is equal to g of f of t minus g of f of x, well, this is equal to g of s minus g of y is equal to, this is just equal to g of s minus g of y, right? So this is equal to f of t minus f of x multiplied by g prime of f of t minus plus v of s, not minus, plus v of s. Well, and this is equal to, well, f of t minus f of x from the first part is equal to t minus x times f of t, sorry, f prime of do I see f prime of t? That should have been an f prime of x. Prime of x. Okay, so this becomes t minus x times f prime of x plus u of t multiplied by g prime of y plus v of s, and as t goes to, therefore as t minus x goes to 0, therefore h of t minus h of x over t minus x when t minus x is not equal to 0, this is equal to g prime of y plus v of s multiplied by f prime of x plus u of t. Okay, and now by continuity of f and by continuity by continuity of f and differentiability of f at x u of t, f at x comma g at y, we have the result. We have the result, right? V of s should go to 0 because it is differentiable. Similarly, u of t should go to 0 as it is differentiable. So the total thing goes to 0, and I have that the result is g prime at f of x plus multiplied by f prime of x. Okay. So example. Now, hey, assuming derivative of sine, assuming sine of x is defined some way, and derivative of sine of x is equal to cosine of x, we can show if f of x is equal to x sine 1 over x and 0, x not equal to 0, x is equal to 0. Okay. For x not equal to 0, f prime of x is equal to sine of 1 over x minus 1 over x cosine of 1 over x. Okay? Because the derivative of 1 over x is negative 1 over x squared, which by multiplication with x is going to give negative 1 over x. Okay? However, at x is equal to 0, the theorem does not apply. The theorems no longer apply, as 1 over x is not defined is not defined, right? However, if you use the definition um, of uh, however, however, from the definition, from the definition, we see f of t minus f of 0 over t minus 0 is, well, at 0 I've defined it to be 0, right? So I get this is just sine 1 over t, which is not defined, is which limit is not defined as t goes to 0. Okay, so we can say f prime of 0 does not exist in this case, right? Even though the theorem can't say it, therefore f prime of 0 does not exist. Even though the theorem cannot tell me that, I can actually show that it does not exist. However, that's not always the case. Even though the theorem might does not work, sometimes the derivative might exist, as we can show from this. Let f of t, well, f of x be defined by, instead of x times 1 over x, x times sine 1 over x, look at x squared times 1 over x, sine 1 over x when x not equal to 0, 0 when x is equal to 0. Okay. Then we obtain f prime of x is equal to 2x sine 1 over x minus cosine of 1 over x when x not equal to 0, and at x is equal to 0 we have f prime of x is equal to 2x sine 1 over x. Sorry, just writing the not equal to 0 part again. F of t minus f of 0 over t minus 0. Well, this time this is equal to t sine 1 over t, right? However, this time you can actually show that this is smaller than or equal to absolute value of t. So it is in fact bounded, right? Letting t go to 0, we see f prime of 0 is equal to 0. So even though I've not defined sine x for you guys yet, if you know what it is, and if you know some of the properties that, oh, maximum value of sine of x is 1 and stuff, then things work out. Okay. Note, in B, in the example, f prime is defined everywhere, but not continuous. Continuous at 0, as cosine of 1 over x is not defined at 0, is not, well, does not go to 0. 1 over x does not tend to 0 as x tends to 0. Okay. Let us do mean value theorem and then stop for this one. The mean value theorems. Mean value theorems. Okay. Mean value theorem is nice. It is the standard other half kind of thing of intermediate value theorem. There are two theorems with names, intermediate value theorem and mean value theorem. So you have seen intermediate value theorem, now you're seeing mean value theorem. Definition. Now, let f be a real function defined on a metric space X. Metric space X. Okay. Till now, everything was on reals to reals. In fact, I'm going to go back to it, but this definition I can just define slightly more generally. We say f has a local maximum at a point P belonging to X if there exists delta greater than 0 such that f of q is smaller than or equal to f of p for all p belonging for all q belonging to X, q belonging to X with d of p comma q belonging to delta. Okay. Similarly, we are going to define local minimum. Okay. Then term 5.8. Let f be defined on let f defined on A to B. If f has a local minimum or if local maximum, if f has a local maximum, same result holds for minimum, but maximum at a point X belongs to AB, and f of X exists if not f of X, if prime of X exists, then if prime of X is equal to 0. So the derivative at a minima or a maxima, if it exists, is 0. Proof? Proof is going to be relatively easy. Choose delta according to the above definition. According to above definition, so that A is smaller than X minus delta, smaller than X, smaller than X plus delta, smaller than B. Why can I choose such a delta? Well, suppose you found a delta 1 which satisfies the property of the definition, right? But it is either X plus delta is greater than B or X minus delta is smaller than A. Well, take a smaller delta, right? If it works for a bigger delta, then it works for every smaller delta. Okay? So take it smaller and smaller till you are inside AB. If x minus delta is smaller than t smaller than x, then what do you get? F of t minus f of x over t minus x. Well, the numerator is what do you call? Negative. The denominator is negative, so this whole thing is positive. Right? If x is smaller than t, smaller than x plus delta, then, well, once again, because I have the maximum at f of x, the denominator is, the numerator is negative. But now t is greater than x, so t minus x is positive. So I have negative or positive, and so this is smaller than or equal to 0. Well, the first part implies that this f prime of x should be greater than or equal to 0. The second part implies f prime of x smaller than or equal to 0. Right? Therefore, hence, well, I don't need to write therefore and hence f prime of x is equal to 0. Okay? Let us generalize the theorem a bit and work towards the generalization. Theorem 5.9. If f and g are continuous functions on AB, if f and g are continuous real functions on AB, which are differentiable in AB, which are differentiable in AB, then there is a point x belonging to AB. There is a point x belonging to AB at which f of b minus f of a times g prime of x is equal to g of b minus g of a times f prime of x. Okay? Proof. Now, it might be tempting to say, well, I want to show something is equal to 0. What if I try to show just these are equal, right? Divide by b minus a both sides, divide by b minus a both sides. Hey, can I show that f prime at 0 here, g prime is 0 here? The points might be at different places, right? F prime might be 0 at a different point, g prime might be 0 at a different point. So the idea is we will try to show that their difference is 0 somewhere. So put h of t is equal to f of b minus f of a times g of t minus g of b minus g of a times f of t. Well, if b minus f of a is a constant, g of b minus g of a is a constant, so h is continuous on AB, then h of t, so h is continuous on AB, h is differentiable in AB, and h of a is equal to f of b g of a minus g of b f of a. Well, this is also equal to h of b. Okay, great. What does the previous theorem say? Wait, did I miss the theorem? That says about maximum. We haven't shown the mean value theorem. Okay. We are trying to show. Okay, my bad. Okay. So I have that h of a is equal to h of b. Generally, I show things in the other order, so this was slightly weird. So we want to show that h prime of x is equal to 0. Need to show, or enough to show. Okay, want to show h of prime of x is equal to 0 for some x. In AB. Okay. How do we show this? If h of x is constant, if h is a constant, then h is constant. Then h of x is equal to 0 for every x. Then it holds for every x belonging to AB. Right? Otherwise, if it has a bigger value, if h of t greater than h of a for some t belonging to a b, let x be the point belonging to ab, be the point at which h attains its maximum. Okay, we have shown before, but in theorem 4.16, that every function on a closed set attains its maximum at some point. Okay, so it is attaining the maximum, hence then h prime of a is equal to 0. H prime of x is equal to 0 by theorem 5.2. Okay, similarly, if h of t is smaller than h of a for some t belonging to AB, okay, so in that case you can find a minimum rather than maximum, and the same exact result holds. Okay, this is called the generalized mean value theorem, and now we will get to what is classically famously called the mean value theorem. which is term 5.10, the mean value theorem. If f is a real continuous function, if f real continuous function on closed interval AB, which is differentiable in AB, then there is a point x in AB. There is a point x belonging to AB such that at which f of b minus f of a is equal to b minus a times f prime of x. Okay? How do you show this? Proof. Take g of x is equal to x in theorem 5.9. So we have already shown the Hurter theorem first. Now we're just plugging in g of x is equal to x, and the result follows. Okay? Because g prime of x is going to be then 1, so you just get f of b times f of b minus f of a times 1 is equal to b minus a, well, g of b minus g of a, which is just b minus a times f prime of x. Okay? One final result, and we'll finish off the section. Term 5.11. Suppose f is differentiable. F is differentiable in AB. In AB, which is to say at every single point in AB. First, if f prime of x is greater than 0 for every x belonging to AB, then f is increasing. F is monotonically increasing. Monotonically increasing. B, if f prime of x is equal to 0 for every x belonging to AB, well, we said that the constant functions have a derivative of 0. We didn't say the other way around, but now we are. Then f is a constant. So basically, derivative equal to 0 if and only if it's a constant. If f prime of x is smaller than or equal to 0 for every x belonging to AB, then f is monotonically decreasing. Right? How do you show this? Proof. Use f of x2 minus f of x1 is equal to x2 minus x1 times f prime of x for any two x1 comma x2 in AB with theorem 5.10. Okay, and Part A follows from plugging in f prime of x greater than 0. Part B, f prime of x is equal to 0. Part C, f prime of x is smaller than or equal to 0. Okay, so I'm going to stop here. This is mean value theorem. It's a really good theorem, and we have the result that if your derivative is increasing or decreasing, the function is monotonically increasing or decreasing. Sorry. Derivative is positive or negative, function is monotonically increasing or decreasing. Okay, let's stop.